Okay, so in this video, we're going to learn how to take the 5-number summary that we just found and turn it into a box and whisker plot. They're often commonly called box plots. So let's talk about the procedure first, and then we'll do an example where we create one. So, procedure. First, we find the 5-number summary. For the data set. Then we construct a horizontal axis that spans the range of the data. Third step is to plot the 5-number summary above the axis. Then we draw a box above the horizontal axis from the first quartile to the third quartile, and draw a vertical line in the box at the median. I'll fix the Q1 and Q3 here in a second. And then the fifth step is to draw whiskers from the box to the maximum and minimum entries. Okay, so this is just a plain box plot. If you were to take more advanced statistics, they would have something called a modified box plot. A modified box plot actually tells you what your outliers are. We're not doing that. Here, we're going to keep it simple. We're just going to do a plain Jane box plot. So with that said, let's look at example number 3. It asks us to construct a box plot for the data in example 1. Okay, so what I like to do first is get all my data in one spot. So let's do that. In example 2, we already found the 5-number summary. So min, Q1, median, Q3, and max. Let's go and just get those all written here. That way we don't have to keep going back and forth. So we found these in example 2. So 11, 23, and 25. 11, 23, 25, 30, and 35. Okay, so now, that was step 1, getting the 5-number summary. We did that, because we already did that in a previous example. Now, step 2 said to construct a horizontal axis. So let's do that part now. I think my axis is going to be long enough. I need to go from 11 to 35, so maybe I do 10 to 40? Let's see. Make this 10. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so 10 to 40, that's 30. So maybe I do 10. Can I count by twos? 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. I think that's good. Ten, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. Okay, so we didn't need this long big thing anyways. So shorten it up. To like right there. Okay. So there's our axis. Let's label our axis with what kind of data we're talking about here. So what is our data? It's the amount of fuel wasted. So fuel wasted in gallons. Fuel wasted in gallons. Okay. The minimum is 11. So I'm going to come up here, come put a vertical line at 11. Q1 is at 23. So put another vertical line there. Then the median's at 25. Q3 is at 30. And then the maximum is at 35. Okay, so what we did was step 3, where we plotted the 5 numbers above. Step 4 tells us to make a box that connects Q1 and Q3 together. And then draw a line at the median. And then the last step tells us to draw whiskers from the box out to the max and the min. Let's try that again. There we go. Okay. Now, there's our box plot. What I like to do is label these. Say min equals 11. So if you ever see something where it says draw and label a box plot, what I'm doing now is labeling it. I'm saying what all these numbers are. The minimum is 11. Q1 is 23. The median is 25. This is looking atrocious. It's making me aggravated. Q3 is 30. And then the max, $35. There we go. There is our box plot. Okay. So from the box plot, we can, and the 5 number summary, as it were, we can actually get another bit of information. So let's do a little definition here for the interquartile range. Interquartile range, commonly abbreviated as the IQR, is a measure of variation that gives the range of the middle portion middle portion, or about half of the data. And so, simply put, the IQR is equal to Q3 minus Q1. That's all the IQR is, Q3 minus Q1. Now, with this, it can help us determine outliers. A data value is an outlier if it lies below 1.5 IQRs from the first quartile or above 1.5 IQRs from the third quartile. And again, we'll see what that means shortly. Let's actually see what it means in this next example. So example number 4. Find the IQR for the data in example 1 and determine if any outliers exist. Okay, so we have our marching orders. Let's do it now. So the IQR, well, let's back up. So Q1, we said was 23. Q3, we said was 30. So that means the IQR is 30 minus 23, which is 7. That's the first part. Then it said determine if any outliers exist. So on the low end, we need to do Q1 minus 1.5 times the IQR. So Q1 is 23 minus 1.5 times 7. Let's see what that would give us. 23 minus 1.5 times 7. 12.5. On the high end, we have to calculate Q3 plus 1.5 times the IQR. So that's going to be 30 plus 1.5 times 7. 30 plus 1.5 times 7, 40.5. Okay, so now that we know our boundaries, I have to look and see, are there any data points less than 12.5? So go up to where I put them in order. That's the easiest. Is there anything less than 12.5? Yes, 11. So that tells us that 11 is an outlier. 11 is an outlier. Okay, go back to our original data. I need to see, is there anything bigger than 40.5? My biggest number is 35. So no. No high outliers. No high outliers. Okay. So our IQR was 7, which means that our observation of 11 gallons wasted is an outlier on the low end of the data. Since our maximum is 35, there are no high outliers. So 11 is low. It is unusually low. It's an outlier. But 35 is the max. Well, we need it to be 40.5. So there's nothing that's like unusually high. Okay. Notice I didn't just come up to the data and say, yeah, 11 is way low. It's an outlier. I didn't do that. I see a lot of that, like on tests and on homework. Are there any outliers? Tell me how you know. 11's an outlier because it's far away. We're not surfing. We're not hippies. We're not going to say, oh, far out, dude. No. I need a mathematical reason here. Not just, it's far away. Okay, so one more thing that we're going to talk about for box plots, and then we will put box plots to rest. So another thing that we can do with box plots is determine the shapes of distributions from box plots. Okay, so a few different ways we can do this. Let's say I have a box plot that looks like this. Now, keep in mind that what these values tell us is where most of the data is. So this is my median right here. And then this is my maximum. There's my minimum. So if I'm looking at this box plot, it's telling me that there is a lot of data right here. That is half the data in that short span. This is half the data. Half of data. So I have, on the left-hand side, I've got a lot longer of a stretch to do half the data than I do on the right-hand side, which means there is likely some sort of tail before I go. So what shape is this? This is going to be left skewed. I have a tail. Let me make this a bit more drastic here. Whee. There we go. I've got a tail over here, and then the bulk of my data over there on the right-hand side. The tail's on the left, so that's going to be left skewed. Now, let's say I have a box plot that looks like this. See how those look pretty even? It tells me if I were to draw a distribution here, it would probably be a bit more symmetric. The bulk of it's going to be in the middle, and then we kind of have about a quarter in each tail. So this tells us that the data is more symmetric. And then, last but not least, I guess I could label these like I did the other: min, median, max. Let's say I have a box plot that's going to look like this. Okay. Now, this is telling me that this one little bit over here is half the data. And then this piece way over here is the other half of the data. There's our min, our median, and our max. So if I were to think of a shape that this could describe, I'm going to have a bunch of data up first, and then it's going to kind of peter out. So what kind of shape is that? Well, it's the only one we haven't talked about. It is right skewed. So that's how we can use box plots to help us determine what shape the data would be in. Okay, so that is it for this video, all on box plots. Stay tuned for the last little bit of section 2.5.